All right, so welcome to the this month's PICUP webinar, where Shaul Hanani and Sarah McHale will talk about integrating computation into the physics curriculum at the University of Minnesota. Go ahead.
Okay, thank you. Let me see if I can share my screen. And let's kick this one on. Okay, can you see the presentation?
Yes.
Okay. Get a laser pointer. Okay. Thanks everyone for joining. I want to acknowledge particularly the people who are here, who are participating in this project. I believe Ken is online. Alexis is here, and of course, myself and Sarah. It's humbling to be here with many pioneers of computation in the undergraduate curriculum. So the goal, as you all know, is to integrate computation as a standard problem-solving method in the physics major. And the principles we have adopted are that computation must be integrated in all courses, as opposed to in a single computation course or either taught by CSI or taught by physics. And we have also thought that there should be, we don't know exactly what it is, but there should be some sort of a canon that all BSBA graduates must have when they complete their degree. Computation must be integrated into all instruction modalities. Computation skills need to be built gradually and then reinforced, like every skill. Computation is not the goal, but we keep in mind that physics is the goal. Computation is just one more problem-solving method. What is computation will have to be defined and be limited. We cannot do all computation, and we're not striving to be computer science majors. And all of this has to be done in a way that, certainly in a department like ours, it's not enough to sprinkle material here and there. You really have to engage in an institutional change, as I'll describe momentarily. I want to give you a little bit of a background on our program, just to lay the land. Each row is a year 1, year 2, year 3, year 4 of the major. The blue courses are the required courses. The red courses are required math courses. And the brown down in the bottom are electives. We have 14 required courses in the major, and we are striving eventually to integrate computation in all, except potentially for Physics 1 and Physics 2, in which those are shared with, those are service classes that are shared with some thousands or more engineers, and at least for the first stage, which could take maybe 5, 7, 8 years, those we leave aside. We are concentrated on our major courses. I want to pay attention particularly to these 3 lab courses in the sequence. Modern physics lab, it says here quantum, it's modern physics lab, and 2 upper-level classes. There is a core material that's defined for all of those required classes. Some instructors look at that core material, some instructors do not look at the core material, but core material exists for what needs to be covered. Many of these courses are being taught twice a year. So although this is the natural progression, not all students take this in the quote-unquote natural progression. We also have astro and physics majors, and they have various conflicts. We have several tracks within physics. Professional physics is the regular track, and this is what's shown here. But other tracks share many of these required courses, but not necessarily all of those required courses. For example, there's a biophysics track. There's a teaching instruction track, various tracks. Of course, there's also a computational track. You should note that there's no required CSI class here. It's an elective. About 70% students take the elective. which is C and or Python. We do have an elective computational methods class that concentrates on algorithm development, but only about 10-15% of students take that computational methods class. Please do feel free to, I'm not watching the chat, so I'm going to leave it to you and to Marie. Feel free to stop me with any clarifying questions. Some more about the boundary conditions of our effort. We have high instructor turnover. Typically, instructors are assigned for 3 years stints in any one class. Longer period are possible for special cases in which you developed some new material. Shorter period are also possible. Instructors go on sabbaticals, you have to shuffle around. But in principle, every 3 years, on average, instructors change in any given course. I've already mentioned that required core material exists for the classes. By and large, there is very limited instruction-related communication in the school. We have 60 faculty members in the school, and there's limited communication. So an instructor could talk to an instructor of the same class who taught it last year or maybe 2 years ago. But for example, if one is thinking about a monthly discussion about instruction-related activities or once a semester, those don't happen, even not once a year. By and large, there's not a whole lot of communication around instruction. As far as the structure of the department goes, particularly as it relates to education and instruction, the head, there's the head who plays a significant role in assignment for classes, but not an exclusive role. There's a director of undergraduate education, and there's a committee, undergraduate education committee, a committee of faculty, and a couple of administrators that is in charge to help the director with policy questions or revisions to the curriculum. In terms of governance and information dissemination, we have faculty meetings occasionally, I'd say once every 2 or 3 weeks in the semester, not every week. As I said, we have 60 faculty members, so the faculty meeting is not a good place to come to consensus or make decisions. Of course, when we have to have votes about a new faculty or tenure, then people vote. But for things that relate to instruction, by and large, this is not a place to, it's a place to exchange opinions, to bring information to the faculty, but not so much to bring action items or closure on action items. As far as our initial conditions for our process, prior to 2015, there was almost no computation included. Definitely, there were no computation requirements, and students could finish the BS or BA with no more than Excel worksheets. After 2015, the Undergraduate Education Committee has, how should I say, recommended that computation be integrated and has sanctioned MATLAB to be the computation platform. And this has been integrated particularly into this class, 3605, Modern Physics Lab, but also into some upper level courses by individual instructors. That was the extent up until about 2015. So about 2-3 years ago, we decided to embark on a more thorough integration process. I'm just trying to look at the time here and see where I monitor time. Okay. We've decided to embark on a more structured integration process. And so this illustrates the approach that we have taken. We were going to select computation skills, and I will talk about each one of those steps momentarily in more detail. Once we've decided on computation skills, we were going to determine specific instruction topics, map those instruction topics to specific courses, and then develop the instructional material on a course-by-course basis. Here's how it maps in a little bit more concrete basis. Jumped one slide. So we decided on computation skills that we are going to incorporate. We decided on coding, mathematical modeling, presentation visualization, and validation and verification. You'll notice that, for example, symbolic computation is not here, AI is not here. We decided only on what we thought were the highest priority item. So on coding, we decided on a small set of topics, instructional topics, to be included in coding. We're not trying to replace or displace or be a CSI class. And those coding skills, or any skills that I will talk about, or any topics that I'll talk about, are intended to be built across the 4-year or 3-year curriculum, not necessarily in any one, exclusive in any one class. So in coding, for example, we think array operations are important or functions are important. In mathematical modeling, again, it's a very broad, there's many topics that you can include in mathematical modeling. We decided, for example, that linear fitting is important, chi-squared, matrices as examples. Presentation visualization, again, very broad, and we thought about this subset of topics, semi-log, log plots, contour and surface plot. That's pretty much it. And same thing for validation and verification. The next step is to take these specific topics and map them to our specific courses. And so in parentheses here, this number enumerates specific courses where we think it is most suitable to teach specific topics. I should be clear that when we say here 4001 is suitable for matrices and eigenvalues, eigenvectors, this is probably not the only course. Here I'm just showing courses that will be most relevant for this talk, but many of these topics are relevant for multiple courses that are not shown here. And so here's an example for 4001 analytical mechanics. This is now, whereas here in this slide, we're talking about mapping the instructional topics, in this particular case, mapping mathematical modeling into specific courses. And of course, I should say, we map coding and we map presentation. All of those have mappings to specific courses. Here's how it translates to any given one course. So the new topics that we plan to include in 4001 analytical mechanics and upper division mechanics class, for coding, it's for loops and normalized units, and for mathematical modeling are these topics. Of course, the idea is that these new topics for 4001 build upon skills that have already been done in earlier courses in the sequence, and that they enforce material in the earlier courses. Those are not enumerated here. I'm just showing the new topics. But of course, we realize that we build upon and reinforce. And of course, we realize and we recognize that while this seems to be a very linear process, none of this is really very linear. There's feedback, and there's a crosstalk between all the topics. And all of that is fed by an assessment that we have to keep doing on instructors and on students, and we will talk about assessment a little bit later. So here's the implementation schedule as it looks now. This is the fall semester, this is the spring semester. I'm not showing here the summer, and the columns are academic year. We are now at the end of this semester. We started in fall 2022, where we have observed, this was just simply an instructor sits in 3605 Modern Physics Lab, which is a 4th semester laboratory, and just takes notes about how computation could be integrated. The next semester, 3605 is being team taught with two instructors. One is in charge of the quote-unquote regular instruction, and the other helps the first with implementing computation or integrating the computation. In parallel, we do observation in 4001, the fifth semester, advanced mechanics. In the next semester, 3605 is regular teaching. We are just debriefing and learning from what we have done in the team teaching. And then again, another sequence of 3605 team teaching this semester and the final team teaching. So 2 semesters of team teaching. 4001, we had team teaching here, debrief, and then another team teaching there. So that concludes the commitment the department has made for team teaching. And the idea is that after these 2 semesters, we sort of have arrived potentially into hopefully some steady state or a little bit more improvement. But from this point onward, instructors are being mentored. New instructors in 3605 or in 4001 are being mentored by those instructors who have done computation in the past. In red here, you are seeing our plans moving forward to the next couple of years with another pair, I should say, of 2 classes. 2201, we are going down 1 semester to 3rd semester thermal physics and going up to 7th semester E&M. I should point out that we are supported by NSF, and our grant ends in about a year, in about 2 years. So this is how, some examples of how this translates to actual courses. So modern physics lab, it's a lab course. So there's a lab component, a class component, and a homework component. In the first week of lab, we do MATLAB on-ramp, and we do some assigned exercises to help the students catch up with the on-ramp. In class, in meantime, we talk about uncertainty, significant figures, and then mean and standard deviation. Then the next week of lab, all the students do this lab 0, and they practice plotting linear data with errors and using MATLAB to fit the linear data, and so on. I'm not going to go through all of this, but there's another lab, and then homework. You do linear fitting, and you do chi-squared. And these all are meant to have a crosstalk going forward between the class, the homework, and the lab. Here's another example from 3605, a student making a plot in homework 3, and then the students receive feedback, the entire class receives feedback, and a week later in homework 4, that's the same student, and that's the presentation of data as represented and as you expect after some instruction. And another example, same student in homework 3, writing some MATLAB code, and then again, explaining to the students and hammering the point that code has to be documented and explained. And then homework 7, another piece of code, and now the student adds these comments and explanation of what the various variables are. All of this is embedded, all of this academic integration is embedded inside an environment of culture change. You have to have faculty buy-in, you have to have instructor training, you have to have material accessibility, and the material has to be easy to use. And if all of those around or surrounding components are not in place, there's very little chance for the entire effort to be sustainable over many years. And so here's the sustainability. There is already consensus among the department, as there is among many or the majority of US faculty in general, that computation is generally important to include. However, In parallel, what you want to do is you want to keep the project on the radar. So we have gotten into the practice over the last couple of years of asking the department head to report in faculty meetings about the computation integration effort. So that keeps the project on the radar. The faculty keep hearing about this and about our progress. It's very important that the project is not driven by a single person. It's very important that it is a departmental initiative, that many people take part, that many people take stake in it, and slowly you hope that most people will take part. It's very important that the head and the director of graduate education and the graduate education committee will be on board. And you want to avoid faculty backlash. And so I'm showing here a slide from a recent faculty meeting presentation. And I just want to look at those, I want to pay attention to those boldface, where we say to the faculty very explicitly that we do the integration, but we want to maintain the current goals, the physics goals of the courses. We don't intend to overrun the courses with computation. We acknowledge that the material should be easy to use and readily available for instructors. We acknowledge that the integration should be slow and incremental process with continuing support from everyone. So it's very important that faculty don't feel someone is running forward and there's no listening and no attempt to include everyone in the process. Instructor training is important, and we're making our first instructor workshop this coming May, a 3-hour workshop or roundtable. And as I said, the material needs to be easily available, and we are developing a local repository with computation problems, not that different from PICUP. You guys have been way ahead of us with that. But by having it local and sort of nominally easily accessible, we hope it will be more readily available and would lower barriers for instructors. And finally, all of this effort has to be backed by assessment for computation and physics literacy, and to see whether students and faculty, to assess the attitudes of students and faculty. So this is a great point of time to move to Sarah, who's going to talk to us about assessment.
Hi, everyone. I'm a physics education research graduate student at the University of Minnesota, but I'm actually in Norway where it's the middle of the night. So if you see me yawning, it's only because it's very late. But like Shaul said, he just kind of contextualized the broader change effort associated with this. And what I'm going to discuss is that beyond just attempting to implement a change, we also want to understand what the ramifications of this change are for the students. And this is important because physics is already a self-selecting community. And when we're undertaking change within our community, like integrating computation into the teaching of physics, the changes that we make have the potential to broaden access points to and engagement with physics, but they also have the potential to do the opposite. So throughout this process, we want to ensure that integrating computation into physics courses isn't detracting from students' abilities to understand the underlying physics in the course. Because first and foremost, these are physics courses. And we also want to make sure that we're monitoring how this course might, or this change might be shifting students' perceptions of physics and of their own abilities, making sure to look both at the cultural impact of teaching physics and with computation as well. We also want to make sure that we're collecting evidence that will allow us to assess whether the computational educational goals are being met in student work, if we're actually reaching the outcomes we hope to. And we want to gain an understanding as to how this curricular change is manifesting in ways that help students develop beliefs about what a computational literacy looks like in physics and what that means, as well as how they reflect on the literacy that they're developing in this course and how that's supported. And so we also want to make sure that we're gaining insight into how being in this class impacts how students also view themselves and what it means to be a physicist seeing if they view themselves as physicists with a redefinition of this. So next slide, please. So the way we're going about studying this is through a mixed methods case study design, where we're focusing on the first two courses that Shaul mentioned that are undergoing this process. 3605, which is Modern Physics Lab, and 4001, an upper level mechanics course. And so we have been and still are collecting data from fall 2022 up through the end of this semester across a variety of modalities. And so I will go into detail on each of these. But for a quick overview, the type of data that we're collecting is through pre and post course surveys, where over these 2 years, we expect to have about 100 total respondents per course. We're also making sure to collect exams and other coursework to get evidence of student work that they're producing. We're also conducting interviews with students in the course and professors twice a semester, and making sure to include the TAs as part of these interviews as well to get all different players in the game associated with this. And what we want to do with the interviews is to try to go through and characterize how the changes are intended to be manifesting and what actually the impact of them is, to try to trace how this change process is leading to specific outcomes in specific ways. And what will really help us for that is the fact that we're doing some course observations from a research standpoint to try to look at the different components of the course. So next slide. So let's get into each of these components more specifically. The surveys that we're administering are all administered as part of typical course operations. It's pretty normal for students to take surveys in our department because there's a physics education research group. And so we have them take 4 surveys at the start of the semester and 3 at the end. The difference in number is only because this demographic survey, we only have students take once at the beginning. We also administer a learning attitude survey developed at CU Boulder. And this measures how closely students' beliefs about physics or if their physics courses align with expert beliefs on something called a Likert scale. So what happens on this survey is that students see a statement and they choose the extent to which they agree or disagree with it. And they get scored based on a score that experts got when they took that survey, reflecting an attitude about learning physics. We also have a self-efficacy survey that was also developed elsewhere. And for a quick definition, I like to think of self-efficacy as positive confidence. You can believe in your ability to fail, and that is confidence. And you can be correct in predicting that, but we want to look at students' belief in their ability to succeed in a physics course. And so that positive confidence is self-efficacy. And this is also measured through a similar scale where students are seeing these different statements and choosing the extent to which they agree or disagree with specific statements. And then here at Minnesota, we've been in the process of developing another instrument that's mixed methods and gets at students' beliefs about and experiences with computation before entering the class when administered as a pretest, and then during the class administered as a post-test. And so the types of questions that this includes are, again, these statements that students respond to. We have some open-ended free response questions and a few rating or ranking questions where students prioritize specific things. So I'll briefly talk through what some of these different analyses look like. So we can go to the next slide. So when we look at our learning attitude survey, when we look across the 2 classes we're doing this in, you might notice first and foremost, we have 3 semesters of one course and 2 of the other. And this is just due to the staggered timeline that Shaul mentioned in his diagram. And so the first semester for each of these are kind of more of a baseline observational. And then we begin to start to integrate computation and perturb the curriculum a little. And so in here, basically what we see is that all of our error bars are overlapping for this, which means that as of right now, when we look at the raw averages on this course across the class, we're not seeing a significant shift in learning attitudes. It is important to note that typically, for this survey, actually, over the course of a semester, scores tend to go down. And so here we're actually not seeing a really significant decrease, which may be something positive. Next slide. So our self-efficacy survey, on the other hand, we might be starting to see some evidence of things. Again, our first semesters are more or less controlled, just the way things were beforehand. And there we see actually some non-overlapping error bars when we look at our averages. And then for the next 2 semesters or the next 1 semester, we see some differences here. And so these are all really slight changes. So we might be starting to see some changes, but again, we're only looking at some descriptive statistics of raw averages. And we really wanted to get some other tools to look at different ways to investigate what's actually going on. We have a variety of different means that we're using to collect data to get information on this, as well as other more complicated analyses we can use. But just taking the time to look at these raw averages helps us do some good baseline real-time monitoring to see if we're having huge differences across semesters and if we need to intervene really quickly and make some changes to mitigate issues. Next slide, please. So for our computation questionnaire, like I mentioned, this survey is more mixed method. And so we have a variety of different types of questions. And so I'm just going to give you a small window into this through 2 open-ended qualitative questions. And so in these questions, they're back-to-back, and we ask students to describe when they're using a familiar software or computational app, how they choose to learn a feature that they've either never used before or have forgotten how to use. And then in the next question, we ask them the same thing, but about a platform that they've never used before. And so the way we analyze these responses is we had student text ranging from a short sentence to a paragraph, and we would go and look through what students say and try to find different themes. And so we started just looking for patterns across this and eventually found that in the first semester of the modern physics lab before the effort was implemented, so this is fall 2022, 2 primary categories were surfacing for student responses. We called these self-guided and externally guided. So the self-guided students were in charge of what and how they wanted to learn. This often came up through the form of playing around or seeking out quick solutions to very specific items. Whereas the externally guided students were looking for an expert, a specific person to use, or an entire plan that would be more robust. So let's look at how this actually manifested in the data. Next slide. So when we look at this 1 semester, again, this is pre-change effort, we noticed that for the familiar software, just over a quarter of students were using external guidance and the rest were kind of relying on themselves. However, when we ask them about unfamiliar, it looks at face value like there's only been a really small change. There's only 2% more students who report externally guided, probably along the lines of 1 more student. However, when we look not just at the raw numbers and instead tracing individual students, and looking how these individuals move between familiar and unfamiliar, the data actually reveals something slightly different. Now, in this case, just under half of students still remain self-guided regardless of familiar or unfamiliar platform usage. And we see a pretty small fraction remains external, about half of that original group. And then we see that the other half of the external group shifts to now being self-guided, whereas now we have about a quarter of the class total that's actually moving to prefer external guidance. So what does looking at the data this way do? By asking these questions in the semester before we went about implementing this change, this helped us gain an understanding of how students want to be supported in this, and to also reckon with the fact that students who have different comfort levels with the specific platform use chosen might need different support mechanisms, because we want to make sure they're having a positive experience in the course and taking their desires into consideration as well. And so we found it helpful to try to consider, even if students do have experience through some prerequisite courses, we found that already in this case for the students beforehand, about a quarter of them still wanted this guidance. And in our class, we want to just make sure we're able to provide the amount of scaffolding and support that students need to experience success. Next slide. So these were just some kind of quick looks at the instruments. What are we planning to do longer term? For our quantitative instruments, we're planning on taking these responses and matching different participants on the demographic markers from our demographic survey, as well as matching them on pretest scores. And then we're going to be able to look for differences in the tests, both between the overall distribution of scores and if the medians or the averages in this sense differ, to see if there's a different impact on different subpopulations. We'll also repeat that same process for final exams. But first, what we have to do is try to see if the physics content is comparable. And so there's been a physics problem difficulty rubric developed at the University of Minnesota that we're planning on modifying for this computational context. And so we'll take paired questions to ensure that the assessments are comparable across semesters. Again, trying to match participants and see if there are differences in certain groups being more impacted in this change than others. Next slide. So the bulk of what I'm actually focusing on for my dissertation is qualitative data that we're collecting to get at the last components that I talked about, which were the development of computational literacy and physics identities. And one way that we're gaining this insight is through interviews with students. And so in this, what we do is we interview about 5 to 6 students per course, twice per semester, for about an hour each. And we choose our participants based on a thematic analysis of their responses to the open-ended questions on the computation questionnaire. And we do this to make sure that we're getting a wide variety of student viewpoints about computation, and to make sure that we're talking with students who have different prior experiences with computation, so we can gain more insight into how they're experiencing the course. We also make sure that we're overrepresenting students who are marginalized in physics and in the course, so that we can see what the equitable impacts of this are on the course experience. And our questions in the interviews ask about how students are feeling in the course and about the course, the relationship that they view between physics and computation, and the extent to which they identify as a physics person and what that means for them. Next slide. We also interview all professors and TAs of the courses involved in this change process, also twice per semester. So once at the beginning and once at the end. And our questions for the instructors ask now this time about their own experience with software. So we can see if that's playing a role in the way that they feel about teaching with computation, how they interpret and both implement the goals of the course, how they feel about the course changing over time and what that may or may not do for the course culture. And we want to get at their attitudes about involvement with this change effort and about their role as instructors, looking at the role that they think computation plays both in the field of physics and in their teaching, how students learn best, and focusing on attitudinal climate components, as well as what they change effort. Next. So we also want to make sure to try to gain a robust understanding of this. And so what we've been doing is also conducting observations of lecture, lab, and discussion components of the course as they fit into the courses. And we do this so that we're able to explain what the culture of these classes are, in line with some pre-existing theories from physics education research. And this helps us contextualize the interviews and bring in different sources of information that can help confirm, clarify, or complicate what we're finding out in our interviews. And our observations focus on how people are interacting both with each other and with their environment, and the things that people do and say or choose to not do and not say, and how those impact the role of the classroom. And so for the observations, we collect data while we're doing this through the observer taking notes in these settings, and then later going back and reflecting on the notes, unpacking them in some memos, journaling, thinking about the different themes that are showing up, and continuing this iterative reflective process throughout analysis. Next slide. And so the interviews and observations come together through an analytic method called conjecture mapping. And in this, what we do is we're trying to take a learning community and map specifically what's happening in this community, in this classroom environment that helps students reach specific outcomes, perhaps differently than others. And so what we do is we start with a conjecture, which is effectively a high-level hypothesis about how learning and identity formation are supported in a specific context. Then we look for an embodiment of how the learning environment is manifested, often through concrete structural decisions that an instructor is making or ways they're choosing to reinforce learning. Before we can jump to the outcomes, which are again related back to our conjecture, our hypothesis about what we think might or might not be going on in the class, we have these mediating processes that explain how the curricular design is related to the outcomes. And this is through the learning activities that the students engage with. And so the strength of this method is it helps explain the processes through which these variables are related and helps us look at differences between design-based impacts and the ways that these outcomes are being reached. And you can imagine what we're able to do is then trace these patterns across this map. And so we can then look for ways in which certain components are reinforced or why certain outcomes are reached more strongly or differently than others. Next slide. So for a very quick overview, this is kind of a little bit of a sketch of what our process looks like. So we get our hypothesis and embodiment from the instructor interviews. We try to look at the decisions instructors make, looking at the professors in terms of the curricular decisions they make and how the TAs implement that. And then we ask the students for how they feel about the different outcomes. And we bring these together by looking at the activities that the instructors believe students are undertaking and what students report doing in the class. And we try to trace these different threads throughout and look for sources of continuity or discontinuity. Next slide. But like Shaul mentioned, it's really important for this all to be iterative and for our change to be communicated back to our instruction, or for our findings from research to be communicated back to the instructional team so that we can implement change that works. And some examples of the ways in which that's manifested so far is that the TAs have played a pretty crucial role in this process, and instructors have chosen to bring them into the conversation by specifically asking their TAs in these courses for challenges that students are facing. And one way that this has surfaced for the students in the class is that as a result of hearing feedback about student difficulties with the platform, professors have included more language-specific support in the course through onboarding activities, computational templates, and shared experiments to practice coding while doing physics. We also had a summer where we had a TA continue over as a curriculum development TA to help translate some student frustrations with lab manuals. And this editing allowed for the coherence of a lab manual to really help reinforce these computational goals through specific directions and making sure that the analyses were scaffolded for different times of the semester. And this also allowed us to help recalibrate the labs to students' level of knowledge and to make the labs more culturally responsive for students. And last but certainly not least, we hosted some feedback sessions with the instructional teams after preliminary analysis of interview data and observations. And so we wanted to make sure that our findings that were emergent in the data were communicated to these teams with enough time to be able to implement changes based on what we've been finding. And one thing that surfaced was a slight tweaking of the team teaching model from how it was initially implemented based on the way it was landing for students. So again, we just wanted to really make sure that we're tying this all back in, right? The purpose is to help implement this as part of a sustainable change. And so we want to make sure all of our research associated with this is circling back. And I'll hand it back to you, Shaul.
Thank you, Sarah. Okay, so I just want to summarize. We have started a process to integrate computation throughout the physics major curriculum. We're working with 2 classes. We're doing all the assessments that Sarah talked about. The department here in Minnesota is prototypical for some large departments across the country. So we think some of the lessons we learn are likely transferable to other institutions. Thank you.
Great, thank you so much, Shaul and Sarah. And I will open up both the chat and the floor for questions for them.
Should I open the chat or do you want to mediate that?
I can mediate for you,
Okay.
but if people have questions, feel free to also unmute yourself and ask the question. And while people are thinking, maybe I'll start with the first question, and that is that, change does take time. It takes, the first class that you make a change in, students will say, well, my friend who took this class last year or last semester didn't have to do this. And so there might be some resistance in that way. And then they take the class, right? And then the students a semester behind or a year behind. So it seems like it takes maybe 3 or 4 years before now this is the way that the class is, and that change is really integrated. And I know that you're only about a couple of years in, but have you seen some of this? Have you seen both a little bit of resistance and then kind of the normalizing that this is the way that the classes are now?
So, I think there are two prongs, two answers to this question, Maria. My main concern is not the students. I know I'm not answering your question, but I will answer momentarily. My main concern is not with sustainability with students. If instructors will maintain sustainability, if instructors will maintain the curriculum we're planning for, if instructors improve upon that, the students will adapt and they'll be fine. And maintaining sustainability with instructors, in my opinion, that's the key challenge. Now, back to your question, have we seen some student resistance to begin with? I think, for example, in 4001, when we had done the co-teaching last semester, there were some student comments about the way the co-teaching had been done that didn't quite work smoothly. So we have seen some feedback and some reactions to that, but it was not specifically a reaction to computation. In fact, the computation itself, the students were pretty happy about and enthusiastic about. So I can't say that we have seen negative student reaction in the sense of, hey, why are we doing this? Students in past years didn't need to do that. Nothing of that type.
And 4001 was classical mechanics, yes?
Yes, it was, advanced classical mechanics, yes.
Yeah. Well, and what I'm saying works both ways, right? Because if the students now expect there to be computation in the class, then that also is a little bit of pressure on a new instructor to also add computation into the class.
In fact, in classical mechanics last semester, the first quiz had a computation component. When we got to the second quiz, we couldn't quite manage, for whatever reason, we couldn't manage a computation component, and the students complained. Why do we not have a computation element in the second quiz?
Yeah,
so
it is now expected.
It is now expected, exactly. We told them there will be computation, we're doing computation, blah, blah, blah. And now they say, hey, why isn't there computation? We want computation. Okay, yeah, so we made
a question from the chat. Could you talk a little bit more about how you plan to deal with turnover in instructors, and how do you plan to help future new instructors maintain the computational components of the classes?
Yes. So there are two components to this. This is a real key issue. There are two components. The first component is that we are working with the director of undergrad studies and with the head to ensure that computation-friendly instructors will teach the computation-infused courses in the near term until everyone comes on board. So we're very specific about, for example, in these two courses that we have done, not to assign instructors who are known to oppose the effort. And, within 60 faculty, there are always, few instructors who, they think whatever needs to be done, they know better. That's fine. Maybe they do know better. But so that's one component, to assign instructors who would be willing to work with the mentors. And so the second component is the mentorship. There has to be a mentor to go along with the instructor and to say, here is what we have planned, here is what we have done for this course, and this is the reason, because it builds upon previous courses, because it prepares for the future courses, because we don't want instructors to do just whatever comes in their mind. It's perfectly fine for instructors to develop new problems, for example, or to have initiatives, but around the material that is part of the full curriculum. So to reiterate, there are two key, and the third component that I should mention is the instructor workshop and instructor roundtables that we are now initiating to bring as many instructors as possible, to bring them up to the plan, to explain to them that there is a plan, and to get their buy-in into this entire process.
Another question from the chat. How long do you anticipate that it will take to integrate computation throughout the major?
Infinite time. Because it takes infinite time to implement any instruction if you really want to do it properly. There's always changes, there's always improvements. But infinite time, I know, is not a very good answer. Realistically, I expect it to be at a minimum 8 years, 10 years. I think by 15, we are reaching steady state. I think.
Okay.
At least.
And one more question from the chat. What fraction of the faculty have to be computation friendly to thoroughly integrate?
Yeah, that fraction is a function of time. After 15 years, I think we need to have 90% computation friendly. And so the idea is that that fraction increases with time. Right now, and also the idea of computation friendly is a little bit fluid. As I said, most of the faculty, the largest majority of the faculty, not only here in Minnesota, but I think nationally, agree that computation is important and somehow should be incorporated and implemented. How to do it, in what fashion, in what way, this is where the difficulties arise. So that's one element of computation friendly. The other element is computation friendly in terms of hands-on expertise. I can actually assign to my students, and I can oversee the grading, and I can be creative with, for example, new problems. So there are various elements for computation friendly. That second element, I think, is a cultural shift that comes with time. Essentially, the vast majority of the young faculty are computationally friendly on both elements. They know Python. They know that it's easy for them to do MATLAB if they need to do MATLAB, or maybe they'll push us to go to Python. Whatever, it doesn't matter. The platform is really irrelevant here. The young faculty are all on board, and they are friendly already. The older faculty, I think many of them are friendly in concept, but for example, the instructors with whom I worked last semester in classical mechanics, he was not comfortable with the hands-on part of actually authoring either a MATLAB or Python. He's very enthusiastic about this, but I don't know what I need to do in order to do this problem or that problem. So that element will take time. I hope that by 10, 15 years, we won't have any of these challenges anymore.
All right. A couple of questions for Sarah. One is really quick from me. Have you thought about also engaging alumni in some of your surveys? I know it's a couple of years still ahead, but to get some feedback on how this prepared them for their future careers.
Yeah, no, that's a fabulous idea. And I think something that could help, see, is this playing a role in the careers students, choose to go on to do, or the success they find there, or perhaps even, in finding summer research opportunities with a new skill. So it's definitely, something worth looking into. The question is, when and how, and what does it take to create a new instrument and all that fun stuff.
Yeah, and one more for you, Sarah. In your research, were there any particular findings that you found surprising?
Yeah, so I mean, I think one thing that stuck out to me is I think it often can be tempting for us to people who are more familiar with computation to view it as a sort of language agnostic approach. But for students, I've been finding, especially in interviews, that students who have prior computational experience don't always find the transition to a second language so easy. In many ways, they know what to be upset about. And they make mistakes about syntax and they want to code the way they know how to code. They don't want to code in a manner that's specific for the strengths of a specific platform. And so trying to find ways to account for that has been, challenging because I think they come in with a confidence that can carry over and help them, transcend a lot of immediate frustrations. But what do we do in trying to help them, you know, do that? It's not as straightforward as we think when someone knows how to code, intuitive or as easy a carryover for students as we might think.
All right, thank you. And that does bring us to the top of the hour. So I want to thank Shaul and Sarah again for a great presentation, and thank all of you who are here for a great conversation as well. And we will be posting the recording up on the PICUP YouTube channel so that if you have colleagues that you think might want to benefit, or colleagues that might benefit from hearing this, you'll be able to send them the link. Keep in touch for future PICUP events. I hope to see some of you in some of future PICUP webinars and in person at the AAPT and APS meetings. And again, thank you very much for a great night.
Thank you, everyone. Thank you. Bye-bye.
Thanks.